Hello, hello, and welcome to our latest work, Further Insights into Coupled Characteristic Modes. The work has been recently presented in IEEE INCAP 2020. So, basic agenda of this today's presentation are theory of characteristic modes, theory of coupled characteristic modes, corresponding results and discussion, orthogonality of theory of coupled characteristic modes, error analysis of TCCM, potential applications of TCCM. Before jumping into TCCM, let's talk about theory of characteristic modes, which have been proposed by Harrington et al. Based on the method of moment integral equation matrix. Before that, there is a formulation for electric field theory, but the current best formulation is the most popular one. Before characteristic mode analysis, method of moment technique was developed by Harrington to solve any arbitrary object in its corresponding current density vector like this, where V is the excitation vector, G is the method of moment impedance matrix, and I is the corresponding weighting vector of the equivalent current density. So if Galerkin's matching is followed, then this G matrix will be complex symmetric, and its real part will be a positive definite lossless structures. The conventional antenna design problem was generally following this workflow, where we specify a particular excitation vector on a certain object or antenna, which gives you the current density following this equation. Once you get the current density, you know the electric field and magnetic field due to that current distribution. Now, if we show this serial computation process of method of moment, then every object current needs to know the excitation vector. Then only we can understand its current density or electric field, magnetic field. Characteristic mode analysis actually decouples this problem into two parts: excitation independent part and excitation dependent part here. If we see here, this method of moment matrix is independent of the excitation vector. This provides this excitation independent parameter. This is the lambda n, that is the innate eigenvalue, and In is the innate characteristic current mode, and En is the innate characteristic field mode. Now, the total current or total field depends on this V vector. So what does it be counted for? So here there is a coefficient called modal excitation coefficient, which considers both In, lambda n as well as this V vector. So we'll show how those are related here. Total current is a linear combination of individual characteristic current modes. Similar happens for the field here. Now, how do we compute this characteristic current modes? That is from the generalized eigendecomposition of this Z matrix. So you can see here both X and R are symmetric matrix and real symmetric, and R is positive definite. So this eigenproblem can provide a set of n number of eigenvalues and eigenvectors, which are real in nature for lossless structures. So how does the uniqueness of these eigenvectors are depend? So generally it is related to the orthogonality relation. So general orthogonality relation is looking like this. It is orthogonal over the R matrix space and X matrix space like this. Now what Harrington defined, that he defined this each of this PRN, that is this product where M equals to N, that is set as unity. So if that is not done, what's the problem? If you can see here, let us consider any other eigenvector that is a weighting coefficient, weighting vector of this In, like this here. So that is also In tilde equals to some weighted version of In, which also supports this characteristic equation you can see here. So for different values of Cn, there can be infinite possibility of these eigenvectors. So we have to define the uniqueness in some sense. There are multiple ways, as I told. Harrington has assigned the eigenvectors which produce this modal power we call, that is modal radiative power, that is 1, like here. So other way MATLAB actually provides, if you go there, you can just compute the eigenvector and normalize with respect to maximum amplitude. Step like this. So any one will be fine. So what is the difference for different cases? If we follow the Harrington's thing, then this will be like this, the modal weighting coefficient. For other all cases, we have to consider this expression where P are getting this. So both will give us the actual current and field same because the scaling is done here itself. Now this goes for the isolated object characteristic mode. If there are coupled array like this, let's consider two elements for simplicity. Each individual element has certain characteristic modes like this. Now let's consider each element is discretized with n by n matrices. So this is a n by n problem. Now where each eigenvector can be defined using this orthogonality relation. So since it's a n by n matrix dimension, so complexity order using normal techniques like Gaussian elimination, it will be order of n cube. Now following this approach, if we compute the total coupled array, the relation is like this. So this matrix dimension is 2n by 2n because there are two elements. So if you apply the conventional characteristic mode analysis, then its complexity will be in the order of 2 cube n cube. Now if there are instead of two elements, if there are n number of elements, it will be order of u cube n cube. So the complexity is increasing in the cubic order. That's a huge expensive operation for large arrays. There are thousands of antennas are combined together. So what theory of coupled characteristic mode does, instead of solving such large matrix, we compute these coupled characteristic modes in a linear combination of the isolated modes. So this isolated mode can be solved in an n cube problem. So whatever the large array it is. So this linear combination involves certain coupling parameters like these two or two elements. You can express those coefficients using this following equation. So the theory is given here. You can check it. Such multiple examples are there for verification. So this problem is a general solution, that is M to N interaction problem. That means that all the M modes are interacting with all the N modes. But in practice, each antenna has a very few dominant modes. Those only interact among each other to create the dominant coupled modes. So we can simplify this problem in terms of M equals to 1 and N equals to 1. That turns out to be a 1-to-1 interaction. Similarly, for 2-to interaction, it looks like this. So the advantage is that this general problem can be further simplified if we go like this lower